Our next speaker is John Shelton. He comes with experience as the San Joaquin Basin Ecosystem Restoration Program Coordinator. He's also the department's Central Region Water Planning Lead with Integrated Water Management Planning, and works in developing projects and programs that have the potential for environmental water and improvements to water quality. He's also the technical lead in discussions with water users, environmental NGOs, and other state and federal agencies for the San Joaquin tributary settlement process. John? Did I miss anything?
Nope. Okay. That's good enough. More than good enough.
This one?
Yeah, SalSim. Next one down.
Awesome. Okay.
See, Greg was nice to me. He loaded mine up for me. I was going to say, oh, I'm going to mess that up. So thanks for staying so late in the afternoon. As Greg kind of went through, one of the things he didn't mention that I'm a modeler, because I'm not. I am consider myself an ecosystems sort of person, but I don't do modeling. But our department has worked on the SalSim model for nearly 10 years now, and so I wanted to go ahead and give an overview of what this is and give you a little idea of where we're at on this. There are a lot of management concerns. You could read through these, but I kind of want to throw out even a bigger idea. You've gotten this so far during the day-to-day. The San Joaquin system is very different than the Sacramento system as it comes into the Delta. South Delta is very different than the North Delta. San Joaquin system used to be a very significant contributor to the Central Valley salmonid population, especially the spring run. It used to do 200,000 fish, adult fish returns. The spring run is mostly gone now, except for the work we're doing on the main stem at this point to bring them back, and a few individuals we see every now and then. Fall run is very low compared to what it used to be. A big part of the reason we think from our department that we've worked on this, and others I think support this, is if you look at the flow and the hydrology of the San Joaquin. When you look at hydrology for most systems, when you start exporting or diverting 20% of the water to 25% of the water, you start seeing significant impacts. We export, divert from the system before it goes on down, usually 70% of the water. So we have 30%. Most of that 30% actually comes in the very, very wet years, and so most of our years are actually very low water years. So when Brad was saying on his model, when you look at flow considerations, we do think on the San Joaquin system that the flow is a huge component of what goes on, and this is what drives a lot of the issues. So it goes back to a little bit of what Gary was talking about on what's causing the mortality. Is it predation or something else going on? So we have worked as a department to also get the State Water Resources Control Board to list the San Joaquin system as temperature impaired. We have some high temperature issues. A lot of that's low flow issues. A lot of it's just because we have high ambient air temperatures that drive the system, and a long flow from our rim reservoirs down to the delta. So these are the things we're battling. This management challenge slide shows a lot of the different regulatory processes that we're in the middle of now, and so this is part of the reason we put this thing together, this model. Lots of very tough questions that are out there. As I think you found out as a panel today, there is lots of data that's out there. There is lots of information going on. The synthesizing of it still has a long ways to go to be able to fit it all together. And as we all know as scientists, that the more you find out, the more you want to know and the more questions you have. So there are still lots of big questions out there. The project team, make sure I gave credit to where credit is due. Dale Stanton and Dean Marston are the top and bottom of the active role. Those are the Department of Fish and Wildlife people that are on this. The rest are consultants or academics that have helped us through this program very much. But we also have a list of, I wonder if I'm going to get there it is, the supportive role. We have quite a few more agency people and others that have contributed both to the biology, ecology, to the data, to helping us go through this system. I am in the support role, but I'm even a smaller bit than all these folks. I helped off and on, but not as much as these folks have. So the model goals and objectives. Our first real big objective was to develop a fishery planning tool. We wanted to make sure that it informed the flow decisions that were in front of the State Board and others as we went through. We wanted to make sure we had broad scientific community acceptance, and it advanced the fishery science. We say it is advancing with the idea that we knew we weren't going to answer all the questions. We wanted it to be something that was useful. We also wanted to have broad management utility and confidence, broad spectrum of accessibility. Our intent is for anybody who's interested in the code, we'll be able to get you the code on into the future, and you'll be able to work under the hood on this thing if you need to. But with all that, also that accessibility, we wanted to make sure it was web-based and completely accessible. So it is on the web now. We are still working. We rolled it out about a month and a half ago, so it's brand new on the web. But we also wanted to make sure that we had all the background information, everything else on the website so you can see that. That is still in the process of getting there. The evolution of this is part of the reason I have this up here is to kind of give you an idea of where we started from. Back in 2005, the State Water Resources Control Board asked our department what would happen if there was more flow in the San Joaquin. We had some ideas, but we weren't solid on those ideas. And so they pretty much challenged us to put together a model based on flow. Our original model was a very simple model, spreadsheet model. We did go through a peer review on that on the version 1. And coming out of that peer review, we knew we needed more work to do on this. We already knew it before going into the peer review, but we wanted to make sure we captured what the first peer review said and tried to make our model better. We actually did it in 2 phases. We did an early model contract. We put together the preliminary model results. This was to address the peer review, but we also addressed the responses in there, and some of those responses were, we need more time to even capture some more of the earlier peer review information. So after we got through this process, we actually rebuilt the model into now what we call SalSim. So, but it's the early version 1.1. We've moved up to 1.5, 1.6, and we're finally in SalSim. Sometimes you hear it referred to as version 2.0. We think it's a major change from the earlier ones. It took us a while. We had some contract issues because we ran out of some bond funding. We have also sent that through peer review, and I believe you guys have that as part of your literature. And that peer review, we have addressed the issues coming out of that as best we can, but we also wanted to get it out and put it out to the public and get the use of it at this point. On into the future, we want to continue working with this, work with the agencies, work with others who want to put together on this stuff. And our hope is to continue to upgrade this as we go through, definitely through data, but maybe getting under the hood and doing some other work, or potentially have somebody else take it on as their deal. So the idea is this is the beginning of a good tool, but it's not the end all of the tool. SalSim overview. SalSim is an integrated system-wide model. We are looking at the full system from the rim reservoirs, not upstream of the rim reservoirs, but we are looking at temperature in the rim reservoirs as it moves on down through the riverine system, through the delta and out to the ocean, back through the delta and back up to spawning habitat. It contains 3 submodels that are important. There's a water operation model. The water temperature model, we used HEC 5Q. HEC 5Q we actually rebuilt on a parallel process, an application for basin-wide San Joaquin on HEC 5Q, and we think we have a very good application of that. This is one that we started on the Stanislaus early on. We then made it larger to hit the Merced and Tuolumne rivers, and then the last version we actually included the Friant sub-reach, so the reach from above Merced on down, from Friant down to the Merced confluence. So it's a basin-wide HEC 5Q model of temperature as it goes through. And then it contains 3 interrelated geographic areas, the inland, the delta, and the ocean. A little diagrammatic of that. One of the things I did want to show was that the water operations, water temperature model feeds into SalSim, or the salmon model itself for the fish production. You can put in specific data, but you can also have external data sources that you can load into the system to run the model. And then what comes out, you have a graphic interface that you can see what's going on right at the time, but you can also get a DSS output file or CSV output files and do what you want with the data. There is a tremendous amount of data that's generated each time you take a run through this. Again, the geographic area that we're talking about, Friant Dam, on down, confluence, we get each one of the tributaries, we do the delta, and we do the ocean. I wonder if, yeah. And that just highlights the different rim reservoirs. Rim reservoirs, the temperature data that's in there, they are actually put into the HEC5Q so that the rim reservoirs are modeled, and so what's coming out of the rim reservoirs is from the models of the reservoir. Another way of looking at the design, we have the three modules, I guess goes this way, inland module delta and the ocean module. We also have to try to figure out how to get the adults back. One of the issues with very low flows in the San Joaquin, especially during the fall, is it's very confusing for adults to be able to figure out what the signature of the San Joaquin is. A lot of the water at that point is being pulled across the delta, so it's a little bit hard to figure out what's Sacramento water and see any trace at all of the San Joaquin. And so we do have a homing module. We also have, this is Merced River Hatchery. We do have a hatchery component, and we, in the model, we do split up the native or the naturally spawned and the hatchery spawned and how this works through the system. The inland model, I guess I'll go through each one of these as we go through. The inland model, I don't want to touch all this stuff because I know it's late in the day. I don't want to get to all the details, and I don't know all the details that well, but the development and survival factors, flow, water temperature, density dependence, and then also predation areas. So predation areas is the idea that we know mortality and others happen at different rates through different parts, different reaches of the river. So we don't really have a predation component when you're up in the tributaries themselves. Movement factors, one of the things that we have, as a lot of the resources agencies has looked at the San Joaquin, and we've kind of figured out that we've changed our concept of how we try to do work with the salmonids. You know, I think in most estuaries you'd like a salmon young to get down into the estuary, then grow big, and then get out to the ocean. With our system on the San Joaquin, and I think Brad and a few others have kind of mentioned it, we look to see how fast we can get the fish out because there is so much mortality through the system. So we actually, with our movement factors, we have a slow, medium, and fast cohorts that makes a difference on their survival. That includes the velocity of flow, temperature, and floodplain encroachment. So we do have GIS information on floodplain and acreage of floodplain is flooded for different flows. For the San Joaquin survival module, so this is the main stem of the river. In this area, we again look at flow and water temperature. We don't really have a predation effect in this area. We basically get them through the tributaries, and once we get into the main stem, they get down pretty quick from there down to the delta. Movement factors, velocity and flow, including rate of change, and again, temperature. So the delta module, this is probably the one you're most interested in. We do have survival factors, inland inflow to the delta, water temperature. Again, water temperature is very important to our fish because our temperatures can get high very quick. Most of the time they can get lethal, but a lot of times they are suboptimal, and so we do have that sliding scale in there. Water exports is important to the model and runs into the system. For our predation, we have striped bass abundance is the main area it runs into predation for the whole thing. We had also looked at some other numbers. Striped bass abundance was the main one that drove for anything we were doing on the San Joaquin. And then head of Old River, it's HORB status, if it's in or out. If it's in, then the fish are more likely to go down the main San Joaquin, and if it's out, they have a good chance of going on down towards the pumps and can get picked up state and federal projects. So the ocean module, we have lots of information, data from sport fishing, trolling, ocean conditions such as upwelling, and that all gets fed into the model and gets us a return on adults later on. And we do break that out by cohort, so we know what's going on the different age classes that are coming back in. So the only other thing I wanted to say is again, I did mention I'm an ecologist. SalSim's on the bottom down here. This table was put together by one of our models who worked on this. And one of the things that we don't really have the ecology explicitly put into this model. It's a flow model, and it's based on the relationships that are built from the flow. But we do believe right now that we integrate a lot of the data, that integrate a lot of the things that are going into it when we look at the flow. And as we move on into the future, we may be able to get some submodels and other things that can capture some of this other information as we go through. So we're not done with this. We want to get it out there as a useful tool. And that was my last slide. So, questions?